This chart shows the hidden physical cost of how we interact with the internet today. A traditional web search requires about 0.3 watt-hours of electricity to process. But ask a generative AI model to write an email or summarize a document, and that demand jumps to nearly 3 watt-hours, almost 10 times the energy. On its own, 3 watt-hours is negligible. It is less electricity than it takes to charge a smartphone. But when you apply that computational cost to billions of users asking billions of questions every single day, the cumulative power draw becomes massive. The cloud is a heavy, physical machine. It relies on millions of square feet of concrete walls, miles of thick copper wiring, and rows of industrial chillers to prevent the servers from melting down. Artificial intelligence software is advancing exponentially, growing faster than almost any technology in human history. Yet that limitless digital growth has run headfirst into a very hard physical ceiling. Over the next few years, U.S. data center demand is projected to double. Tech companies are no longer planning standard server farms. They are designing gigawatt-scale campuses that require as much electricity as the entire city of San Francisco. This timeline compares our two distinct development cycles, and you can see exactly where the math breaks down. A hyperscale AI data center can be designed and built in 2 to 3 years, but designing, permitting, and building the high-voltage transmission lines required to power it takes 7 to 11 years. Because the electrical grid cannot expand fast enough, utilities rely on an interconnection queue. Right now, nearly 1,400 gigawatts of capacity are stuck on a multi-year waiting list just to plug in. That backlog is roughly equal to the entire installed electrical capacity of the United States. You cannot fuel a software revolution that scales exponentially with infrastructure that scales linearly. The timelines have completely misaligned. The delay is compounding because the physical supply chain is strained to the breaking point. Connecting a massive facility to the transmission network requires heavy industrial transformers like this one. Currently, the waitlist for this basic electrical gear is upwards of 3 to 5 years. Even if a data center secures the hardware, AI behaves differently than traditional cloud computing. A server hosting websites draws a steady, predictable amount of power. When an AI cluster begins training a new model, it ramps from idle to drawing hundreds of megawatts in a matter of seconds, a phenomenon operators call grid gulping. Those violent power swings create subsynchronous oscillations. They can literally tear the physical steel blades of a power turbine apart. The legacy electrical grid is already struggling to expand, and the literal physics of how we generate and transmit power are incompatible with the erratic, massive electrical demands of training artificial intelligence. With the grid severely backlogged, tech companies cannot wait a decade for new transmission lines. Solar and wind farms are too intermittent to support systems that must run 24/7. So Silicon Valley is making a desperate pivot to the most reliable baseload power available, nuclear energy. To bypass the grid queue, Microsoft signed a 20-year agreement to resurrect Unit 1 at 3 Mile Island, committing to purchase all of its generated power for their exclusive use. Amazon executed a similar strategy with a 1.9 gigawatt agreement at the Susquehanna nuclear plant in Pennsylvania, buying a data center campus directly connected to the reactors. The tech giants that built their empires writing code are now operating the heaviest, most regulated physical infrastructure on Earth to ensure their own survival. Moving directly next to a power plant secures electricity for the tech companies, but it pulls that exact power away from everyone else. This strategy of co-locating at existing reactors has triggered intense scrutiny from government agencies. The Federal Energy Regulatory Commission recently rejected an amendment for Amazon's Susquehanna deal. The commission cited severe concerns that removing that much baseload power from the open market would force everyday citizens to absorb the resulting grid upgrade costs through higher utility bills. Regional operators are also stepping in to protect public supply. PJM, which manages the largest grid in the U.S., is drafting rules that would force massive new data centers to face power cuts first during electrical shortages. What started as an engineering bottleneck for developers has rapidly escalated. The mismatch between digital ambition and physical reality is now a political crisis threatening the reliability of the public grid. This diagram illustrates Jevons paradox. As technology becomes more efficient, lower costs trigger an explosion in demand, resulting in more total consumption. This traps AI. While engineers reduce energy per prompt, cheaper models cause query volumes to skyrocket, demanding vastly more net power. The tech industry argues that they need this massive compute right now to build the AI models that will eventually optimize our aging smart grids, manage renewable intermittency, and help solve climate change. That leaves us with a high-stakes timing problem. The crushing energy demand to train these models is happening today, while any AI-driven grid optimization is likely a decade away. Can artificial intelligence optimize the global grid fast enough to survive its own voracious appetite?